Wait. Sorry, guys. I was just... Something seems different. But I can't quite put my finger... Where are my fingers? What's going on? Why am I so small? Okay. The last thing I remember, I was at my computer, getting ready to talk about plate tectonics. I think I fell asleep, yeah. And when I woke up, realized I was going to be late. I ran here, and now this. Well, I feel okay, so let's do this, and I'll deal with all of this later. Right. What was I going to talk about? Icebergs. What do icebergs have to do with plate tectonics? Well, we know that when ice freezes, it expands because of hydrogen bonding. It becomes less dense than the original water. We also know that ice floats in water and looks like this. But why? Based on what we know about density stratification, less dense material should just sit on top, like when we made our density columns. Nice, neat layers. And the ice should just be the top layer, right? But ice sinks a little. Actually, ice sinks a lot. In fact, 90% of an iceberg, or even an ice cube, is underwater. Only when it sinks to this point will it then float. You already know this, but it should actually seem a little weird. Now, this is because solids interact with fluids differently than fluids do with fluids, like in our discussions of water and air masses. Yes, less dense solids will still float, but instead of being stratified, there's something called buoyant. And buoyancy is the ability of an object to float in a fluid by displacing a fluid volume equal in weight to the object's weight. Seems like an awfully complicated way to say it floats. So what this means is that the object doesn't necessarily have to be less dense than the fluid. Ooh, tell me more, tiny plastic professor. All right, let's say I have this nice ball of material that is more dense than water. If I drop it in water, it sinks, and well, I guess I don't have it anymore. But if I get a new ball and I change its shape, so voila, the same material that is more dense than the water, but I've changed its shape. Now, if I put it in the water, eureka! So what I did was to change the shape such that the same material with the same density and weight now takes up more volume. When it begins to sink into the water, it displaces or pushes aside some of that water. And that water pushes back with a force equal to its own weight. That's buoyancy. So, if the weight of that displaced water is equal to or greater than the weight of that object, then the forces balance and it floats. Pretty neat, huh? This is why giant ships made of thick, dense steel can still float. It's also one of the physical properties of Earth that will help us answer our question about the differences in age between the Earth and the ocean sediments. This is fun and all, but I think before we continue, I'll go see if I can make myself a little bigger and a little less plastic. So grab a snack, and I'll see you back here in All right, last time I gave you guys a bit of a riddle, right? I showed you this figure here and I said, why is it that the oldest sediment, so again, 161 million years, and like I said, this little area right here, let's just say 190, is so much younger than the Earth, right? The Earth is 4.6 billion years old. So why that difference? And you guys had to answer that, and like I said, most of you, or many of you, right spot on, and a lot of great answers to think about how this goes. And the simple thing is, it moves, all right? So the Earth moves, these continents move, things change. So while a lot of these rocks are that old, the ocean floor has not always been there. In fact, if you do a quick calculation, so like I said, let's just take that spot, that 190 million years old, and 4.6 billion, and a little bit of math, tick, tick, tick. You can say that, all right, well, in the present form that we have now, the way the continents look, well, if we backtrack, we've actually had like 28 completely different looking Earths, all right? So just stuff that, there's continents, there's ocean, like I said, the ocean's always been around, but they just look very different. All these processes are incredibly different, the way the currents move. And to get there, yes, they move. So how do they move? Well, first of all, let's go back to this figure. And, we go all the way from the center of the Earth out. And this becomes important for this because while we're talking about the crust, it's the crust that moves. And it's because of the structure of the Earth. What do I mean by that? Well, last time we talked about the structure of the inside of the Earth. And we talked about it all the way from the core here, all the way to the crust. And I kind of blew by and said, okay, well, we have a couple different crusts. There's oceanic and continental. Well, the way this shakes out, if I show you this figure, this is kind of blown up on the crust, is we have continental crust here, mountains and stuff, and then oceanic crust here. Well, just below that, all right, is the rigid part of the mantle, and those all together are called the lithosphere. And they sit on top of that more plastic asthenosphere, right? The movable, still solid, but movable part of the mantle. Well, what do you notice about this? Why is it that this whole thing dips down? There's a mountain, it sort of dips down and sits kind of sunken in. Well, this goes to what our beginning of this lecture talked about, and this figure should look pretty similar. All right, and this is an iceberg floating in the ocean, and this is what we talked about, buoyancy. So really, what we're looking at is we're looking at the crust, or actually the whole lithosphere, floating on top of the mantle. It's buoyant. All right. What I mean by that, let's take a look. Sort of the same thing, but like I said, this is based on density, right? So here's our big continental crust, and then on the sides are some oceanic crust, and these are actually density numbers. And you'll see that continental crust, 2.7 grams per centimeter cubed ish, and oceanic at about 2.9. I mean, they're kind of close. Oceanic crust is a little more dense, but importantly, the mantle is 3.2 grams per centimeter cubed, so it's more dense. So that means buoyantly, the crust is going to float on top of the mantle. So that's the first thing. The crust floats, right? Or at least it rests on top of the mantle, and it creates those depressions like we saw. But something else is the crust isn't one solid thing. So actually it can break apart. All right, and these are where we get into what we call tectonic plates. So these plates wrap around the globe, all right, and there's breaks in here where you see these cool, I didn't do this cool light coming out of it. I don't really think that would happen, but it looks neat, right? But really, if we take and we look at a figure like this, and we're going to kind of stick with this figure, it's going to be really important. The surface of the Earth is broken up into about 12 major tectonic plates, all right? And they interact with one another and they move. And it's the way they interact that makes this all possible. So, like I said, you can see the divisions of these plates, and we'll talk about each one, the way they move. So the way they interact is in three main ways, okay? They interact by coming together, moving apart, or sliding past one another. And they do this in a special way. So I'm gonna kind of show you how these things move. Let's first let's picture like a conveyor belt, all right? So this conveyor belt, it's moving along. And what's really happening is this is what's going on underneath. So it's not like, the continents are necessarily floating towards each other, but the whole plate is moving. So if I take a bit of both continental and oceanic crust, so they take the lithosphere, it's going to move along, all right? It's going to move along this treadmill, and that's what's going on. So like I said, because of this, they're going to interact in different ways because, again, sometimes plates are going to collide, sometimes they're going to move apart or just move around. And the first way they're going to do it is something called a divergent boundary. So these are all going to be boundaries we speak of. And divergent means they move apart, so plates moving away from each other. So if we picture two of these treadmills, and they are moving away from each other, all right? And this is where we get a divergent boundary. So here in the middle is where new molten material is going to come up and move to the side. So you get something like this, okay? You get this, you see here a seafloor spreading. So this is where new crust is being formed. So that crust is coming up, and then these, the lithosphere is moving apart. And you're going to find this in places like here. This is a mid-ocean ridge, and there's several of these all over the planet. I'll throw another figure you can see there in your lecture notes that kind of points out the ones that are moving apart, the ones that are moving together, and the ones that are sliding. So keep that handy while you're looking at this. But this happens here. This is the mid-Atlantic ridge. This is a massively long mountain chain, all right? And it's a mountain chain because that new material is coming up from not the center of the Earth, but from the mantle and forming new crust, and it moves apart. So these are going to, drift this way. All right, that's important again for a few other reasons. So these kind of circle the Earth, these mid-ocean ridges. In fact, you can see this in places like right here is Iceland. All right, so that you notice that mid-Atlantic ridge goes right through Iceland, and Iceland was born out of this new material coming up, and so it's still growing. Iceland's getting bigger and bigger. And you can sort of see here, there are places where people can go and stretch across. No, it's not this massive volcanic activity. This is really slow, but they can stretch from one side to the other. And this isn't just standing in a ravine. This is one person's touching the, this giant North American plate, and another person's touching this giant Eurasian plate. And oh, by the way, something really cool, if you happen to scuba dive, this runs right through some freshwater lakes in Iceland. And you can go down and you can get in between the fissure, and just like this, you can touch Eurasia and North America underwater. Pretty cool. Something else is this is how ocean basins are formed, all right? So kind of look here, you can see how these pieces fit together. And oh, by the way, this is how they, kind of started figuring out something was going on. This eastern coast of the US fits snugly there, while South America fits snugly up here into Africa. And that's how new ocean basins are formed. So this started as just a fissure and grew and grew and grew until the Atlantic was born. And we can see this in places like East Africa. So you see this kind of red line here running through East Africa, and that's the East African Rift Valley. And what that means is that's a spreading center, that's a divergent boundary that is moving. Eventually, this is going to be a new ocean. All right, this part of Africa is going to move off out here. You're going to have a new island out there next to Madagascar. That's Madagascar. And this is going to be a new ocean. So Africa will be split, and there'll be a sea in between. Okay, what else? So those are some of those features. So that's a divergent boundary. This is where new crust is being formed and the plates move away from each other. Well, if they move away from each other, they also have to move towards each other. So again, if I take my treadmills here and they're now moving towards each other, they're going to have to go down. They have to go somewhere, right? We don't just fade into nothing. And this happens in three special ways. So a convergent boundary can either be a continental crust and an ocean crust coming together, two continental crusts or two ocean crusts, all right? And we'll go through each one of these, and they form different things. So a lot of this is based on density, like we said before. So let's say, for example, we have a oceanic crust and a continental crust coming together. Well, what's going to happen, we already said the oceanic is more dense, so that's going to slide below. It's actually going to move below that other crust, and we call this a subduction zone, okay? And what can happen, as you can see in this figure, is then we get these mountains, right? There's some volcanic activity that happens at a certain place below, and we get mountains. So importantly, if you guys look here along the coast of South America, that's a massive convergence zone. So this entire oceanic plate is moving underneath South America. And what happens is you get the Andes Mountains. You get this massive mountain chain all along a continent because of that ocean-continent convergence. All right, well, next, I said you could have two continental crusts coming together. Well, they're both not very dense, and they're not going to sink, so they're just going to collide. And maybe you guys have heard of this, but this area right here is the Himalaya Mountains, right? The largest mountains in the world. So what happened is you see on this plate here, there's India, and it came and it slammed into Asia, and it just pushed the continent up and created mountain chains. So when a continent and a continent crust collide, they're going to create mountains. And finally, you have ocean and ocean. Now, these are both dense. They're not going to both subduct. So something important to remember is the older the oceanic crust is, it actually gets a little bit more dense. So what happens is the older crust, so if we look back out here where we said this little area here is like our oldest sediment that we know, about 190 million years. And what that means is, there's some very old oceanic crust out there, and it's actually going to move below the other oceanic crust. And you're going to get a few important features. The first one is it's going to create the deepest place on Earth, ocean trenches, okay? This is that, we talked really, really early in the semester about how these can be up to like 11,000 meters deep. So out here in the Mariana Trench, like about right there-ish somewhere. It's not really zoomed in, but you can get a trench. And you also get a couple other features. You get something called island arcs. So the same thing when the crust goes below another, you get that area of volcanic activity that's going to bring new material to the surface, and in this case, create underwater mountains, and they're going to they're going to form island arcs. So what you end up with is out here, Japan and Indonesia, and all this stuff out here, these are actually volcanic islands formed because of this activity, because of a subduction zone. What else? So finally, we do live on a spherical Earth, so things can't just move away or move towards. Sometimes they have to slide past each other. So if I take now my two treadmills and I put them next to each other, we can see we're going to get something called a transform fault, where two pieces of crust, or lithosphere in this case, actually slide past one another. And this is going to give you things, pretty violent earthquakes also. So places like California, right? The San Andreas Fault. This is where we have that transform fault of these lithospheric plates moving past one another. So that's a pretty good picture of all these things. So all these areas you see here, and again, go look at your figures, you'll see some more, but we have three different types of boundaries. We have divergent, right, that new ocean basins form and those big ocean ridges. We have convergent, which can either be ocean continent, continent continent, or ocean ocean, forming a lot of those features, so island arcs and ocean trenches. And then we have transform faults, the ones that slide past each other like the San Andreas Fault. Okay, great, we have this picture. But it's not just knowing how they interact, but how do they get the power? So a lot of the class we've discussed the energy required and the mechanisms to do things. And this is going to be the same. So where does the energy come from to move these massive plates? All right, well, let's take a step back, something we've talked about a few times. And if you guys remember these hydrothermal vents in the bottom of the ocean, all right, we've already talked about how, the chemosynthesis that happens and the organisms that live down there. And we also kind of glossed over the fact that this is hot. This is really hot fluid. So, while the ocean is about 4 degrees Celsius, there's 400 degree water coming out of here. Well, that's because it's incredibly hot below. All right. It just so happens that these hydrothermal vents occur mostly in these spreading centers where the mantle is fairly close to the surface and gets very, very hot. And in fact, if I take a cutaway of the Earth, so this is back to our cutaway, so down here is the center of the Earth all the way out to the outside, well, there's a temperature gradient, all right? And that temperature gradient looks something like this. So up here on the surface where we are, it's nice and nice, I guess, as it has been all semester. And as you move down, the temperature goes up. In fact, if you get down here to the center of the Earth, we're looking at like 6,000 degrees Celsius. That's about the temperature of the surface of the sun. That's incredible. So really hot down here. And what does that mean? Well, we already know, based on ocean currents, that this difference in temperature is going to create something called convection. And even though this is solid material down here, obviously other than this outer core, but solid material in the mantle, it's still going to create convection currents. So what happens is it's warmer below, and it's going to heat up, and it's going to rise, and then it's going to cool off, and it's going to move back down. So because of these currents, you get these massive churning of this solid rock, remember, and it's going to push these plates apart. Now, this is a bit dramatic, but this is an amazing graphic, and I couldn't not show it to you. But what you can see here is just those currents are creating those spreading centers, and also they drag other crust down with them. So you can sort of see, go back to this one, you can see where, this bit of lithosphere is being subducted. So it's actually being pulled down to into the mantle to be recycled. So that's where that comes from. So that's the power, that heat, those convection currents inside the planet. Okay, well, that's great, but I don't know about you, but it doesn't really feel like I'm moving. If I go outside, look at those people standing in the middle of the fissure, or me swimming in the fissure, we're not moving. So how do we know this? In fact, this happens so slowly that just to look, you would never see it happen. We had to measure it. But to even measure it, we had to have some sort of evidence that this was occurring, and that's what we can see. We can see historic evidence. We can see the leftovers of this occurring over the billions of years that it has. And I'm just going to touch on this. There's three main ways that we can see this. One of them, of course, the sediments that we've already talked about. But also, this churning of the Earth's mantle does something else, and it creates a magnetic field because of the metals that are in there. When they start spiraling around, they'll actually create a magnetic current. What that means is the Earth actually acts like a magnet. It has its own magnetic field. It has a north and it has a south. Right now, the north is near the North Pole and the south is near the South Pole. And I just said right now. Interesting. It's not always that way. So your compass works great now. You go out and it's going to point north, but that's not always the case. Sometimes it points the other direction. And that happens really fast. So it stays in one direction for quite a long time, but that reversal, we call that magnetic reversal, that happens within a human lifetime. That's pretty amazing. That's basically like, right now your compass works and maybe in 20 years it doesn't because now the North Pole is in the South Pole. Anyhow. And we can see this evidence. So what happens is when that, say, let's take one of these spreading centers, well, all that molten material that's coming up, there's little bits of magnetic material in there, this iron magnetite that's in there, and it's free to move. So it's going to align itself with that North Pole, just like a needle on a compass. Well, if I look at this figure, once it actually comes up and cools, it's stuck. All right, so those magnetite materials are stuck pointing in the direction of north. So in this figure here, you can see, this kind of brown, its colors are terrible. This brown area here is normal. So that's with the north being in the north. That means all those little magnetic materials, they came up from the bottom, they pointed north, and then they stuck that way. Well, when the poles reverse, those little magnetic materials are going to point the other direction. And that's what we can see here. Those are the more colorful areas. So as this occurs, a little bit comes up and you create these bands either pointing north or pointing south. And that way we can tell how this is spread. So if you go all the way back in time here when it first happens, well, this yellow area cooled and stayed that way, and then it gets moved further and further and further. So this moves apart and we can see this happening. So that's one way to tell. And also, by the way, be able to know when this happened. We can take, how old's the sediment there and what direction are they pointing? And we have a pretty good idea when these reversals occurred. All right. The next way is something beautiful and tropical. And anyhow, if you guys have ever been to Hawaii, Hawaii is a great example of this plate tectonics, all right? Sometimes in the mantle, you get these areas of stationary plumes, all right? So this really hot molten material. So this figure here kind of shows that. So this is a, artist slash scientist rendering of what it looks like underneath, and you get these plumes of hot material. And so let's look at it here. So this mantle plume, and it stays there. It stays fixed with that mantle that's underneath. Well, what happens is the plate on top is still moving. So as it moves over, you're going to get volcanic activity, but then it's going to move away and it's going to stop. And you get these island chains. So let's zoom in on this. This is Hawaii here. So right now the mantle plume is, right here-ish, just off the big island of Hawaii. And then as you move north, these islands get younger because originally this Kauai here used to be down here. So you guys see how it moves. It just moves along. And actually the Hawaiian island chain is really, really long. It goes, all the way up in here to somewhere Russia, right? And it curves too. So we can see there's a little notch here where the plate switched direction. So we can see that too. Pretty interesting. The final way is delicious. I only say that because the best analogy I can think of is peanut butter. So what happens if I take a look at, let's say this is a subduction zone. So this is our oceanic to continental convergence zone. And that oceanic's going to dip below the continent. Just like we talked about, there's a mountain range. Well, what happens if there's some continental crust on that moving plate? Well, yeah, a mountain would form, but it's not a whole continent. It's just a little bit. So what ends up happening as that plate dips, this continental bit or crust stays. It gets scraped off. So I said peanut butter because it's like if you take some peanut butter and you scrape it off on that jar and you get that little bit on the edge, that's sort of what's happening. So I'll show you this one. If I look at the western coast of the United States, that's pretty much what it is. So all these different colors are different material that were scraped off as a one plate was subducted below the other. So I think this one's like some island arc material, some submarine deposits, which just means sediment, ancient ocean floor. So there's other stuff and it gets scraped off. So those three things can show us, they're remnants of what has happened. So just like everything we've talked about, building this picture And time, now that we're doing this, is a bit more complicated because we have to work backwards from the evidence we have. Great. So now we can see. Now we can take this figure here of our ocean bottom, and we can see that, along here's the mid-ocean ridge, these giant mountain chains. Here's some deep trenches out here, right? Subduction zones, some more divergent boundaries here. And if I take that other figure of our sediments and I superimpose it on here, you'll see that they line up perfectly, right? All of our youngest sediments are right here. In fact, there's barely any sediment on top of these mid-ocean ridges. And then our oldest sediments are out here where plates are subducting. Great. Well, I'll tell you what, that's pretty much the history of our planet. All right, we've talked about an awful lot. This is all about the oceans, all about those processes, all about the life that lives there. Now we've brought time into this and all this geology that actually makes all of the other stuff possible. Well, one little thing we have left. So we've brought time into Earth. We haven't brought time into us. I use, obviously throughout the semester, we've talked a lot about biology, but we've talked about biology as it is right now. And there's a whole lot of biology behind us. You remember last time we talked about the origins of life were possibly, what did we say, like 3 billion years ago, or maybe a little more. And I asked you this at the beginning of the semester. I hinted to something called evolution. So we're going to move on. Our last topic for this whole course and for this module, we're going to talk about how biology has changed over time. So it wouldn't be fair if I didn't leave you with one last question, one last riddle to do before you're allowed to come into the next lecture. So this time I have 2 questions for you. One is pretty similar to the first one I asked you at the beginning. Right? What is evolution? What do you think it is? And again, no need to look it up, no technical definition. What is evolution? And then I'm going to tack on another one. How does it happen? How does it work? How does evolution work? How do you think that it works? Maybe a little bit of motivation here. It is the end of the semester. It's getting towards the holidays, and I'm feeling a little festive. So I'll tell you what, hopefully you guys are keeping up with these, because if you turn this one in, not only will you get full credit for the rest of the points for class participation, but I'll go ahead and throw another 5 extra credit points your way. So definitely no excuses for missing this last one. So anyhow, you guys take a look at that again. Your next homework assignment is almost due. Hopefully that's going well, or you're studying for the exam and that paper's going amazingly. And I'll see you next time for our last lecture when we are going to talk about evolution. I'll see you then.